Let's talk about the international system of units that we use in chemistry and, in fact, in all of the sciences. Why do you need an international system? Well, the obvious answer is that you can have scientists in different countries communicating results without having to do a lot of unit conversion. So it's just a very convenient thing, but it really has to do with commerce. When everybody was using their own systems of units and people were having to do these unit conversions, there was an opportunity for graft. If two different counties, for example, in medieval times, had different systems of units, someone would sit at the border between them and weigh the goods going from one side of the border to the other. And when they did the conversion from one county's units to another county's units, they'd do it a little bit wrong and skim off some money. So the French Revolution came along, and they guillotined all of those people that were doing that, and they said, look, we're going to have one system of units through the entire country. And it was pretty successful, and the unit system that they chose made a lot of sense, so it spread from France all around the world. And people sometimes say, well, the United States doesn't use the metric system, but that's not true. Scientists and engineers in the United States use the SI system. All right, so why is the SI system so much better than using the system that we're using now? All of the measurements that you make in SI are based on a couple of simple foundation units that we call base units. Say you want to measure a length. The SI unit, the base unit, let's say, is the meter. That's spelled with an ER in the United States. Everywhere else in the world, it's an RE. And it has a symbol or an abbreviation. And it's a lowercase m. The case matters a lot. An uppercase m can mean something completely different when you're writing down units than a lowercase m. So be very careful about that. Now, how big is a meter? It's about 39 inches. If you're used to the English system, that gives you some idea how big it is. It's a little bit longer than a yard. It's really something like 39.37 inches. Do you have to know that? No. I'm going to tell you right now, and think about this while you're going through your reading and through the lesson. I don't care too much about you remembering a specific conversion between a metric unit, an SI unit, or all metric, and an English unit. If I ask you to do that kind of conversion, and I may on the homework or even the test, I will give you the conversion. You won't have to memorize it. But what I do want you to know are metric to metric conversions, conversions within the SI system. So when I say metric system, the metric system is another way to say international system. A metric system is a system of measure that's based on tens. And the SI system is an example of a metric system. All right. So what about mass? The base unit is a kilogram. And its symbol is kg. Now, this is the only base unit that has a little prefix on it, a kilo. The kilogram, the kilo means 1,000. So this would mean 1,000 grams. A gram is a G. A gram is a small unit. A penny, an American penny, is about 2.5 grams. Too small a unit for a lot of commerce. So instead they use the kilogram, which is 1,000 grams. In English, that would be about 2.2 pounds. So you could take your weight in pounds and divide it by about 2.2, and that'd give you your rough weight in kilograms. Now, what about time? That's a familiar unit, the second. It is an abbreviation S, not SEC. And you know how long that is. And we still do use in science minutes and hours. There are 60 seconds in a minute and 60 minutes in an hour. Temperature bears a little bit of explanation. Fahrenheit temperatures are the temperatures that you're used to if you grew up in the United States. Kelvin temperatures are the SI base temperature units, and they have a capital K for a symbol. Now, let's take a look at the Fahrenheit scale and compare it to the Kelvin scale, just so that you get an idea of what Kelvin is all about. Here's a thermometer that's got Fahrenheit on it, and I've drawn in a couple of reference points here. Water boils at 212 degrees Fahrenheit. Water freezes at 32 degrees. And there is a lowest possible temperature. You can get something cold, that nothing can get colder than that. And that comes out to be about minus 459.67 on the Fahrenheit scale. Now, our lab thermometers are usually in the Celsius. So here's a thermometer, and it's on the Celsius scale, degrees C. And where are these reference points on the Celsius scale? Well, the Celsius is kind of a metric temperature scale. They define 100 degrees Celsius exactly to be the point where water boils. And they define 0 degrees Celsius to be exactly the point where water freezes. And absolute 0, that turns out to be a messy number. Minus 273.15 degrees is absolute 0, the coldest possible temperature. Now, there's some problems with the Celsius scale as well. Because it has 0 in a place that you can commonly run your experiments or encounter. I mean, you've been out on days where water is at a freezing temperature. If you've got a problem where you've got to divide by temperature, what happens when you divide by 0? Mathematically, you're going to get something to blow up. I mean, you can't divide by 0. If you try it on your calculator, anything divided by 0 will be undefined. So it's nasty to have a 0 temperature on your scale in a place that you can actually commonly run into it. That's what the Kelvin scale is for. So here would be a Kelvin thermometer. And they said, hey, the Celsius temperatures are good in that they're kind of metric, powers of 10. But let's just shift the scale a little bit. So how about if absolute 0 is at 0 on the scale? Now, what did they do to get 0 Kelvin here? It's not 0 degrees Kelvin, it's just 0 Kelvin. All you got to do is take your Celsius temperature and add 273.15 to it. So, what's my Kelvin temperature at 0 degrees going to be? It's going to be 0 plus 273.15. And what is my Kelvin temperature going to be at where water boils? It's going to be 100 plus 273.15. It'll be 373.15. So they're very different temperature scales. A degree Celsius is the same size as 1 Kelvin. So every time you change, if you go up to 1 degree, that's the same as going up by 1 Kelvin. So that's nice. So all we got to do is take our lab thermometer readings in Celsius and add 273.15 to them. Now, you can make that into an equation. If you want to take a temperature in degrees Celsius and turn it into a Kelvin temperature, you can just add 273.15 to it. I'm going to put a box around that. That's something worth remembering. We're going to have to use the Kelvin scale in a later chapter. All of our equations will blow up. We'll get division by 0 errors in them if we use the Celsius scale directly. So I will use the Kelvin scale, and we're going to need to know how to turn our lab readings into kelvins so that we can do that. All right. So that's the Kelvin scale. And the last unit of the 5 that you need to know is the mole. And it's for amount of substance. How much stuff do you have? If you scoop up jelly beans, how many jelly beans do you have? Well, you could use the mass as a measure of amount of substance, but sometimes you have big jelly beans, sometimes you have small jelly beans. So really what they're trying to do here with amount of substance is count how many particles of something you've got. The mole is a certain amount of particles of something. It's like a dozen. A dozen is a particle counting kind of measure. If you say, I have a dozen eggs, you're saying you have 12 eggs, that you've counted out 12 eggs. The mole is much larger than that. It's something like 6.023 times 10 to the 23rd particles. So it's a crazy large number. This would be a 6 basically with 23 zeros after it. That many particles. Why so large a number? Well, it has to do with counting molecules. And molecules are very small things. We are going to spend a couple of whole lessons on just the mole later. For now, I'd just like you to know that the SI base unit for amount of substance is the mole, and it is abbreviated MOL. And then that's all you need to know.